Is that good? Or 50? You have guidance on total time?
45, 50 minutes.
Okay.
There'll be a lot of questions.
Okay, I'll keep time. I'll probably skip some.
45, 50 minutes should be good.
Okay. Yesterday all went well, so she went to both the museums.
Yeah,
And
she
the
told
bus
me.
was free.
And you
She
came to
told
pick
me,
up
oh,
the
yeah,
phone.
yeah, yeah.
Yeah, I thought, why is my phone, that phone ringing? Which phone is it? Then I realized
I kept it there. It's not my usual algorithm.
no, no, I forget my phone. I
No, no.
keep it there every time I
Yeah,
put
yeah.
it on
Oh,
the
no, I
car.
have those even I don't know, like wallet, key, property,
Yeah, makes sense.
cars. Sometimes I stop advertising. I start just put it in like a pocket,
Yeah.
especially wholesale. Big.
Yeah, mall and all.
Yeah, really big. So mostly will be an A, right?
Hey.
A, right,
But
both are
that
same.
will be thought that we advertise it.
No, no problem. I kind of shifted it more towards A. There's a lot of underlying A. I just
They love show up.
simplified. Yeah, simplified.
Normally the room is so big, I don't know how many will show up. It's just
Yes.
internet. It's only a topic of interest for now.
Yeah, 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 yeah.
People don't come for this, then I don't know what to say.
Oh, wow.
I think they're tickling. 10 more minutes and I will make it.
Yeah, yeah. In yeah, A&M, they have a CSS required class. So it's like everybody forced to come.
Oh, really?
They take attendance.
We used to do that,
Yeah,
but we
yeah, yeah.
stopped doing that
Yeah, yeah,
because
yeah. Yeah, like students have their own like one choice. You seem like what makes you come early? You were there from the beginning. What's your name? I'm Karthik.
Nice to meet you.
how
I'm interested
oh, you
in
are.
another bunch of AI tools, some of our internship,
Really cool.
doing a program, like really breakthrough sort of things for speak for what the AI tools and program those things. Like, so I got really passionate with what the tools. So my friend said this to me, like, you should go. You can either go to, like,
Pretty cool. it's here.
No, it's one of the cameras over there.
No.
Can you see here?
No, it's not.
I think it'll come up.
I posted on the door that everybody's.
It's all up here. I think you need to call the red shirt guy. It was fine. I tested the whole thing.
No, it'll be fine. Riley, you know why the screen went up? It's MAE 201.
Sometimes you cycle through this document camera projector back and forth and you come back. Yeah, there it is.
It is.
Yeah, I can see the light coming.
It just took off.
Let's go to document camera and then come back to laptop.
I tried that already.
Oh, you did that.
It's on already.
Yeah, that's pretty sure. Do they know it's gone?
Yeah, no, they do. I think Charles is looking to see.
It was there 1 minute ago.
All right, let me see if.
Oh, it's coming up.
They are.
Daytime. Their login timed out. Still not on.
Get started. Join. Another minute.
Yeah. He's coming. I didn't do anything. We were just talking and it timed out. It's here. Which of your projector settings?
Switch to the.
Working. Oh, there you go.
Go freeze on it.
As long as it doesn't go now, I'm good.
All right, people are filing, huh?
All right.
Another minute. Okay. Good, yeah, yeah. There should be at least another 40, 50 people showing
Oh,
up.
again, it's gone. Oh. There you go. What did
No,
you do?
just have to.
Oh, I'll just.
See, your thing is timing out.
Yeah. Okay, I'll be watching.
Give it one more minute. Let's give it one more minute. My glasses.
All good? Yeah. Maybe you want
The
to.
recording has already started, so.
Okay.
All right, I think people are trickling in still. Most probably are checking where the talk is. especially our graduate students. It's my pleasure to welcome Dr. Karthik Ramani to MAE and NC State. We have this annually, we call it the MAE Distinguished Lecture. We have several distinguished lectures in the department, but they're all area specific. This is the one that where we call in experts in other areas that the other three awards, other three lectures don't thing. So we have the Hassan Lecture in Aerospace Engineering in November. We have the Automotive Engineering based work with Zorowski Lecture in March, and then we have the Heat Transfer Lecture and Ozisek Lecture in April. So the MAE Distinguished Lecture is to catch all the other areas that MAE is also active in. And one of them, as you know, is currently is AI. And that's why it's all the more perfect to invite somebody who's been working on it before it became a fad, AI. So Dr. Ramani has been working on this long before it was called what is AI. And so he has been doing design optimization, you want to call it, or neural networks, or smart design, all this stuff. He has used all this. And now, of course, the AI is the word, buzzword today. But he's been doing this for many, many years. So what you don't see in the thing is that he's been active in design and AI and looking at a variety of new activities relating to the automation, human AI, human computer interaction, if you want to call it. So anyway, he comes with a lot of distinguished awards and recognitions. Certainly, one of the most important things is, of course, that he's a chair professor, distinguished professor of mechanical engineering at Purdue, and also has a courtesy appointments in electrical and computer engineering, which is where he collaborates a lot. He got his undergraduate from IIT Madras, and then master's at Ohio State and PhD from Stanford, all of mechanical engineering. And now he's recently ventured, because of his expertise in playing ping pong, and so he's gotten into athletic AI, and I think he's going to share a few things about athletic AI also here. So I think you're more interested in listening to him than me. So without further ado, Dr. Ramani.
Yeah, thank you. Thank you so much, Professor Srinath, and many of you that I met, Venkat and Yong, Ashok, and several others, Xiaoming, etc. Right, Tim. So I had a good set of meetings yesterday. It seems like this thing seems like it just wants to. I changed the connector, but it still keeps losing my. Let me put it back here. It was good for the first 30 minutes, but physical stuff always fail more than more than digital does. There you go. So let me keep it alive. So I'm kind of going to actually I'm a professor in EC in the last 10 years. Produced equal number of PhDs in ECS and ME, a little bit of an edit to Srinath's thing. So I do have a 25% appointment in EC since the last 10 years. Okay, so that said, right, like we like to mix the kinds of things that are done in computing, in computer science, in particular from the point of view of spatial interaction and geometry, right? So if you strip everything off me and wake me up in the dark and ask me, what do you know? It's going to be related to points, lines, and triangles. Geometry is my basic focus and always has been. So a lot of my talk is going to touch into geometry. For some reason, this thing keeps in and out. But anyway, I'm going to give you a very quick run through what's going on in general, how to think about what the emerging space that is coming out. Real world really often doesn't care where you're coming from, right? But there's certainly a big shift happening because of AI, automating a lot of the lower level programming constructs, algorithms, and so on and so forth, back into the physical side, right? So I very strongly think that mechanical and aero and biomedical and all the things that are integrated here in your department are going to become very important drivers for the future. And it's not that you're taking algorithms from computer science and applying it to engineering. It's more like how can we inspire more fundamental work in computing and computer science and spatial interaction and so on and so forth based on what engineering can drive in terms of requirements in those areas, right? So very quickly, right, I think like miniaturization, on the body, wearables, RGB sensing, scanning, a lot of these things, 3D printing, a lot of these things have gone beyond concept development and prototyping and starting to have impact commercially, right? But I think we are well past the so-called flat world, the digital information age, and we are entering an age of what I call physical AI or embodied AI. For lack of better definition, I think I'm going to make you sort of come up with your own feel for what it is. Yeah, we're sort of losing this thing continuously. Yeah, okay, I think we are back on. Yeah, okay. So very quickly, I'm not going to go through this. I used this slide during a recent talk at the US Senate, but I think the three main landmarks, some of your colleagues were actually asking me, right, what can you think about in terms of what AI is doing now, right? So I think there are three key landmarks here. I would sort of point out to the 1986 backpropagation algorithm, right? Jeff Hinton, and of course, he won the Nobel Prize now. I was very fortunate to work with Jan LeCun in 2008 during my sabbatical back in LA. But basically, what that did was it sort of gave the idea of using deep neural networks and propagate it to sort of allow the network to learn. But also what they showed in their Nature paper 2011, which marked its big advance, was that by increasing the size and the depth of the network, it was able to learn features intrinsically. And initially at that time with a benchmark called ImageNet. After that, you kind of see a bunch of things happened. And actually, Professor Srinath pointed out the role of GPUs in this area. Computing, of course, powered this. And you can kind of see that NVIDIA's valuation sort of has become ginormous, right? The big advance after that is what you're seeing in the form of LLMs and so on, the so-called transformer architecture. And the transformer architecture was sort of triggered by an early piece of work in 2017. And it was, this is kind of becoming a little bit frustrating, but it's, I sort of, let me change that and see if that leads to understanding. It was kind of it behaved very well for the first 30 minutes, but yeah, there you go. I'll work through this hopefully. Yeah, so the transformers sort of changed the game, right? Like, and the idea of attention, which was the core part of it, then became the driver for a model to be able to predict not just complete sentences, but go well beyond it. So I'm kind of going to get back to it in a very different form. I'm not going to be able to explain the transformer architecture, but if you understand probability and optimization and understand how these new architectures are being built, you'll sort of understand it. It really didn't matter to people for a while until they realized, of course, Sam Altman and team realized much later much later time in 2000 and yeah, you can try that. Okay, we'll do that. Thank you. It's a good idea.
Okay, let's see.
This is not connected anywhere now.
Wait, where is this supposed to be?
This is your HDMI. Yeah. So you do.
Oh, this is direct like that. Okay.
You can't get to it without my thing.
See that?
No, it's not connected. It's the whole thing is
connected here.
No, that's my box.
Oh, this is. It's your box.
Yeah, you have to go through this. Now put this here, and
This guy?
it won't. Yeah, you can't do it.
How did you do it before?
Your master. Where is your master HDMI?
This is the master.
Yeah, so that goes in here,
And this is also HDMI. So
and this goes here.
that goes here. Yeah,
Yeah,
that's right.
that was no other
But that
way.
was the old one.
Yeah, there's no other way. You have to go through because I don't have direct HDMI Let's hopefully figure this out. Okay, so I'm going to, yeah, we were good for the first 30 minutes. So let me kind of talk about physical AI very quickly, right? So we're kind of talking about an AI that understands perception, understands human actions in physical world, right? And I kind of tend to call it generative physical AI, right? So idea of, can we use AI that is actually generative in the form of, lack of better things, the transformer model and LLM in the textual world, but sort of extend it to the 3D world, right? Extend it to a world where the generation is happening in the physical spaces. So I'm going to be using some words like augmentation. I'm going to use words like context. I'm going to use words like embodied AI.
He's going to put it in here.
Okay, that sounds good. Yeah, so I'm going to talk a little bit about this very original remarks by a person called Doug Engelbart, which many of you may know. He sort of had the so-called the WYSIWYG system, which developed the mouse architecture for the network, internet, and a lot of his early demonstrations were done in very early time, right, 1968. But what people also didn't know, and many of us didn't know, and I had met Doug a long time ago during my PhD, was that he actually thought about the so-called extended reality, right? So what's the difference in this form of spatial interaction? So this is the first time we are experiencing putting computing on our body, and also the machine is seeing the world like how we see it through the eyes. That makes a big difference, right? Not only it's seeing it how, as we see it through the eyes, it's potentially even understanding what we are doing with the hands and the body, and now with LLMs, what we're doing with voice, right? So you're already seeing translations from different languages that have sort of emerged in using the Apple EarPods and so on and so forth. So we are kind of entering this new generation of so-called, people call it augmented or extended reality. It's gone through multiple ups and downs. I always tell my students when they are graduating that you're going to see a lot of different changes in this area. Of course, now the leaders are different. Meta changed and put their entire company at stake. But I'm not going to talk about the technology here. But basically, I'm going to talk about how do we think about and create physical AI applications at scale, right? Which is one of the big issues. Rather than spending a lot of money in creating these apps and you can't change them or edit them or do anything with them. So, and we sort of envision that there'll be need for hundreds and thousands of such applications. So thank you so much. Yeah, cool. Yeah, that's okay. We are in good shape. Let me go with this. Okay. So yeah, sort of synced into it. So we're sort of looking into hundreds of applications and sort of moving forward, right? I want to quickly give an idea of what we mean by embodied interaction. Actually, all of us throughout the whole day have a bunch of embodied interaction, right? We use gesture, we use activity, but we can extend these, right? We can extend this to computing to be able to help us when we are doing these interactions. And it can go across many, many things, right? When you go to the machine shop, when you go do other operations like welding, but also like everyday life for elderly and so on and so forth. The multiple areas that we can think of that these kinds of technologies can help us in everyday life. So maybe you're taking medicine, it's going to be counting it for you, it's going to sort of aid you, very much like many of the things that we do today, right? And the time is kind of very important here. Right now, we can do a lot of these things quite efficiently, right? Scene understanding, object detection, hand tracking, which we did a lot of pioneering work there. So I want to sort of talk a little bit about that. And we did most of this work before the transformer came in. We were using the transformer. I'll give you some examples there. But also I'll be talking a little bit about embodied interaction. So there are three pieces of things that I want to leave you with. But if you're leaving this talk with one thing, this is the one thing that I want you to remember. It is that when you go into 3D, right, it's not just 2D plus 1D, but more importantly, you have a lot of hidden dimensions, right? A lot of hidden dimensions come from many things we do. And interaction in physical spaces is unlike large language models, which are a finite dictionary. You're sort of projecting a world that the transformer has learned, and it's doing a lot of the things that many of us and others use LLMs every day, right? The more important dimension is the human factor, right? Humans are highly variable and not so predictable. So how do you deal with this? So I'm going to talk about 3 things here. One is, how do we understand how and what people do when you're working on things, when you're working on machines, when you're playing sports or athletics? How do you deconstruct what we do? And secondly, after deconstructing it, can we augment the humans in physical spaces? And if so, how, right? Just imagine a ghost or an avatar which is going to help you learn hands-on work in physical spaces, right? Of course, in this day and age, when we want to sort of re-engineer our manufacturing infrastructure, this becomes very critical to help people learn and do things hands-on, right? So, but more importantly, the critical factor is the interaction between the AI and human, right? And you're seeing this, your ability to steer LLM, control LLM. It's not talking back to you and explaining to you how it's thinking. So this bidirectional interaction between human and AI, and that in-between latent space, which we don't understand yet, how do we control that? How do we put knobs to it, right? So I'm going to break it into 3 pieces. Understanding, which involves tasks, activities, context, etc. Constraints, how do you constrain it? And then intent, which is sort of very ambiguous. I'm going to leave it like that. It's being able to do and project ahead what you're thinking, right? And then how do we use the hands and body there? So this is very early work done by one of my students, Ian, who's now head of AI ML at Upwork. He was so basically what he did was he sort of said, Netflix and others, recommender systems, which Amazon, a lot of these things do very well. How do we extend this to 3-dimensional spaces, right? And for instance, if I start treating the recommender system to become analogous to a post-estimation system, which is very important for understanding what we are doing with our hands, for example, right? Can I complete the geometry of my hands in real time, right? Can I understand what my fingers are doing? And without giving it explicit direction on the structure and topology of my hands, can it understand how my fingers are moving? Can I learn the biomechanics of it? Can I learn the kinematics of it? Can I do all of this just by showing it a whole bunch of hands, right? So that was kind of the idea there. And he was able to actually do this pretty well. So basically what he was able to do, I'm going to take the volume. I'm going to take the... Yeah, I'll talk about it. So basically what he was able to do was to train the system offline. So you could have it train overnight, for example, right? And show it a whole bunch of poses, not in the real world, but with a synthetic hand. And then during real time, at that time, computing, it's not too far, but 2012, right, to 16, a lot of that work was done then. Can we impute and infer the pose of the hand, very much like how the matrix completion works? So pretty much what the algorithm does is in real time, it looks at a pose and it completes the pose. It finds the nearest hand poses that it has seen, and then it continuously interpolates in real time. So in doing so, we realized that the system was actually learning constraints, and it got very interesting. So a little bit of fast forward. So you might ask, okay, I'm doing that for hand moving things, but in the real world, we are interacting with a lot of physical objects. You can't see the hand, but your mind knows where my hand is, right? I was very influenced by the early development in the Kinect camera, which was at that time one of the fast-selling electronic devices. So fast forward a little bit, more of the recent work in ICRA Robotics Conference. So we do complete sentences, and LLM, of course, can not only complete sentences, but it can also do entire way of writing a paragraph based on what you intend. But just going back to the sentence completion area, right? Can I treat my whole hand as a paragraph and all these digits as words, for lack of a better analogy? And then when I mask these, I close this, I can predict the rest of the sentence, right? can I train the hand jointly with a language model? So then I'm building on the language model to predict the hand pose behind occlusion. So essentially, these are all the masked portions of my hand, right? If I do this together with what I showed you before, then we can understand what the hand is doing in the real world. For example, you pretty much know where my rest of my body is. I'm not floating in the air, I'm walking on the ground, right? A lot of those things, right? Can the AI project that? So it turns out you can do this pretty well. And also because we built on existing system, the mask joint modeling, sort of you mask it, you train it jointly, and then you use it in real time. So in real time, it turns out it can work really fast. So I'm not going to go through the math, but basically a lot of AI in this space is simply probability and statistics, right? And then optimization functions and reward functions and so on. So we were able to do a lot of crazy things, right? And so Tianyu's working in Meta now. A lot of my students go to work for these large companies, right? Like so we have a space here where there's a discrete input and a static output out there, right? And here the mug was virtualized in real time, and then like you're manipulating the mug. Can it behave like the real mug, right? So a lot of such questions, right? This is a more funky demo, just making the Coke can burst. But also then you can start making things work in physically plausible ways, like giving it certain kinds of behaviors, right? Hand poses and so on, right? Rather than treating it as a bunch of static poses. I'm going to jump that. So sort of extending a little bit, sort of taking the math away from here, I kind of want to talk about the idea of self-attention and graph convolution. So the idea here is, you're given a human skeleton, right? It's think of it as a graph, but there are a lot of intrinsic relationships between the joints. So you can have similar actions, but doing slightly different things, right? So how can you discriminate between them? So it turns out that we used a very different idea of self-attention and graph convolution. And you can see here, I'll just sort of explain this with the implicit relationships that you have between joints, which are not explicitly represented in graphs, such as when your hand or legs or other things are moving, if you measure the distance between the tip of my hand and the rest of my body, right? So there's a lot of other edges that start appearing. And then if you know how to focus the attention of the compute based on what your body is doing, it can predict and also extrapolate your motion correctly. So I kind of wanted to talk a little bit about understanding human motion behind objects, and can we project it? Can we talk about and in real time understand what the fingers and other digits are doing? But also on top of it, right? I'm going to extend this now to creating such applications. I'll show you some more engineering-oriented applications now, and then I'll sort of fast forward to multimodality, because now we have LLM. So clearly the question becomes, I can talk, I can do, right? Can the AI sort of become a better assistant for me? Can I create such applications quickly just by thinking and talking, right? Not applications where you have to go sit on a computer, work on a mouse, and get 5 computer science people to help you create those algorithms and everything. Can I create all of them on the fly? In fact, next week I'm going to be presenting that. I'll give you a preview of that as we go forward. But more importantly, right, in the real world, we do interact with a lot of physical machines and things. So the question we were asking was not just having the AI like a unidirectional interaction, but can I have the AI adjust to my state? If I'm not able to do something, can it come and help me? Or if I'd ask it to go away, I know how to do this well, I don't need your help. Can it go away? And can it do this in the physical world? So in other words, we want the AI to look at what we are doing, understand our state, understand the context in the environment, which can be done extremely well now with LLMs, right? So we have really, like the large companies have really opened up, right? Oftentimes people think, right, research we do, and then it goes to the real world, and then it becomes real. But contrary to that now, a lot of developments in the real world are affecting us, especially in the area of AI, is going to completely change the nature of research, right? Nature of what we think and do, especially for mechanical engineers. There's a lot of Yeah, it's just the beginning of a huge opening for all of you. Yeah. So given that, right, like can it infer and even predict and adapt to you, right? So we are educators, so we want to help people learn and scaling physical learning, right? Working with machines, fixing things, maintenance, repair, overall. A lot of these things, hard to train people, hard to get them going. Everybody learns differently, especially in the hands-on world, they learn very differently. So can I have an AI assistant help in that? So sort of building on some theories in learning science, based on how we learn by doing, building, how kids learn as they grow up, right? They're not taught everything. They're able to, we went through this. We learn a lot of things just by seeing, right? And sort of building on some of those theories, we developed this AI agent which sort of adjusts to your level of detail. So for example, I'm going to sort of just talk about these different levels of detail, right? Like at the lowest level, it's sort of understanding your subtasks. And then at higher levels, it's sort of like helping you even more. So it's saying, yeah, I think what happened was because of the change in machine, I don't have access to that. Let me see if I can.
Laptop.
Yeah, that's what I'm doing. Let me see if I can. Yeah, we can, let me see if I can get to the, LOD, right? It's coming, no. It's somehow odd. Yeah, it was sort of doing well the first half an hour. I have an idea. See if this works. Somehow I'm not able to get that running. Okay.
Okay, you got the video there. Change it.
Yeah.
Change it.
PC.
Laptop, main computer. Yeah, this
PC.
one. That one.
This one?
Yeah.
Okay. I don't know if this is going to work. But
Style.
okay. Let's see.
Augmented reality has widely been adopted in machine task tutoring systems due to the benefit of its spatial and contextual visualization. In AR tutoring systems,
Yeah, I'm going to kind of jump to the main point here. But basically, the idea is sort of help the user as they are doing these tasks. So you can kind of see, like, when somebody is doing it, sort of knows your state, what you're going to do. You're setting up the laser cutting machine, so it kind of starts giving you some help. And then as you're working, it sort of looks at your state, and if you're completed the step successfully, or if you're hesitating, it understands what your hand and body are doing. And now with LLMs, you can even talk to it, right? It'll understand you even more. And then it's getting to help you to show you the next step, and so on and so forth, right? So it sort of is idea that we have been developing and working for a while. Let me get back to. Okay, so yeah, sort of extending this to other areas, right? We did this for bike repair, for woodworking, and then we wanted to convince ourselves, unlike like selling your own research to yourself, that we indeed can do better than paper, better than video, right? And actually, one of the students who's now in Amazon is he actually demonstrated that you can not only create these types of spatial reality applications at much faster times just by demonstrating, but also in terms of learning gains and others, you can do very well. So it was a fairly rigorous study in terms of comparing video paper and extended reality. Many times people think, what's the idea, right? What's the difference between a video and something like this? First of all, it's immersive. It's watching you. It's looking at you, and it can understand you. And if you can do this at scale, it can change how we do everything. The way I think about it is YouTube will be with you all the time in the physical world, but it'll also be interactive and helping you. A future I see is more spatial and better interactions and better help for us in the real world. So, okay, yeah, it's having problems in this axis, which I didn't think about when we shifted. Let me see if we can come back to. Okay. For some reason. Yeah, curiously, this connection is not the best. Yeah. Yeah, there you go. I got it. Yeah. I think this might work. There you go. Oh, there you go. I think we are in good shape. Okay, I'm going to jump this. So yeah, sort of extending this to working on instrumentation, right? Oftentimes, buttons, knobs, and physical things are there all over. And many of you might remember, how did you learn to work with oscilloscopes and a whole bunch of other things, right? How can we author such applications without creating these types of metaphors working on a machine? Yeah, so we created this metaphor called instrument AR, but here we had a small hand variable to detect contact. So as you are turning it, the machine even detects where you're turning the knob, what it's doing. So it understands the state of the machine by looking at it from how a coach would look at you working on these instruments, right? But more importantly, what we were able to do was we were able to author the entire workflow needed to help you for hands-on tutorials when you're working on digital instrumentation, purely through an expert coming and just demonstrating it. So it takes nothing more than that to do it. But more importantly, I'm going to, again, yeah. It's a more, I sort of was going to, yeah. So here, what we were able to do was we were able to demonstrate agents which are coordinated, where you can go talk to each step and sort of say that, I want to do this, I want you to help me heat the water, pour the cup, how do I make the best grind, et cetera, right? So essentially what we were able to do is create a bunch of agents which get connected more in the back end. And here we integrated the language model together with the application context and scenario. So the language tasks are broken down into substeps, and it instantiates each of the agents for each of the work, and then it coordinates these agents across the application. Let me see here. I switch to this. I'm becoming a juggler here. Yeah, I think we are good here. Okay. So yeah, sort of moving on these directions, right? I'd sort of talk about like context-aware methods for training and learning. So the idea here, which I very strongly feel, is that we're sort of looking at very antiquated evaluation methods and ways in which we evaluate people in this new age of AI. But more generally, if you sort of look at how do we teach them hands-on kind of work, and even more so like move these types of things into machines, right? Into machines that help you do things. How do we understand and interact with the physical world? Of course, we do have a lot of things going for us, right? And the so-called Internet of Things, sensors and other things which are embedded in the machines. So how can we bring all of this together from a learning-centric point of view, right? And so one of the interesting things one of my students, Ananya, she developed was this reverse learning method, which is very appropriate for this, right? So based on learning goals, how do you decompose the learning goals into submodules and into micro steps? And if you kind of now have the agent coordinate across all of these different steps, and it not only can use existing libraries and contents which are becoming pervasive, but also it may be able to create some as we move forward, right? So we did this for welding training, but more importantly, what I'm going to show for you now is I'm going to jump this part in the light of how can we use this for actual physical training. So, and also in actual physical training, right? We are going to be using tools which are really not smart today. So there's a whole bunch of smart tools which have embedded AI and ability to sense what it's doing, like drilling, precision drilling, riveting, and many other operations, right? So training for that is challenging, especially in high-performance applications, right? Like if you take surgery or many of the aerospace applications, it becomes very challenging. So we created this haptic tool where you can reconfigure the weights in such a way that it would reproduce the weight, and not only the weight, the moment of inertia, and therefore also with appropriate instrumentation, it might be able to render haptically the kinds of things that happen. For example, working across different types of materials, right? Can we render learn and render the vibrotactic field? So we actually designed and built, and this is possible now, right? Ability to render high G forces up to like 10 G and so on, using linear resonant actuators configured in such a way that you get the ideal vibrotactile field, right? So I'm not going to get into details here, but the idea is like you sort of learn drilling, like speed, orientation, learn material by putting these sensors on the real drill during the real operations, right? And break these tasks into micro tasks. And then Power Tool, which is now initially configured for, like, you can think of it as a like augmented but virtual reality environment, something in between there, right? When you're actually doing, can you train? So it turns out that across various types of tools, from a drill to a hacksaw to many others, we have been able to render vibrotactile feedback. So what you're seeing is real, what you're feeling is real, and even if what you smell is real, you're tricked into thinking it's real, right? So one of the experiments we are trying to do is moving this into the physical world, right? So currently, a lot of the work is actually using this instrument, and I'm not able to show you exactly the actual aerospace applications that we are working on, but we have a rig which will simulate all the biomechanics of the real operations. And so the machine now on your head can not only see what you're doing, but also help you and guide you to do the operations correctly, sort of going, you can practice a million times on a virtual human, right? Or on virtual things and so on and so forth. So it kind of brings together the idea of more context-aware ability for these AI algorithms to be able to help humans, right? So currently we are sort of working on physical tools which will actually help people do these things in the real world. Potentially not even looking at this headgear and others which are sort of perhaps not needed at all at this stage. We are looking at very simple projection mechanisms on both the physical world as well as into the human, but also overlaying the CAD operations that are needed from CAD, which is sitting inside the computer, into the physical world, right? So I'm going to quickly jump into, we maybe lost some time, but basically I'll try to make it up. So can we predict human motion in such a way that if we give textual commands, can I make the avatar go do these things? So in the past, a lot of these were done by putting a lot of sensors on the human body, right, like the movie makers and others did. So we have been working on diffusion models, which can do both short and long term. So if you want a human to do these things in a virtual world, I can just give it text to do various things. And the attractive thing here is if I'm able to do this with human-like structures, can I just tell humanoids to do it, right? So we want to move this into the physical world. So there's a bunch of work that is going on here. And some of these are architectures, and a lot of AI, comes down to your understanding the foundations for encoders, decoders, and all these attention mechanisms, and being able to build these architectures. Pretty much, a lot of the race is creating more sophisticated and more less compute architectures, right? So we actually did this very recently. So this avatar, you just instantiate it by telling it what you want it to do. And LLMs are very good at decomposing these tasks. So you just go and you show it the various objects. This is a shelf, this is a 3D printer, this is this. So it gets some idea of the context. After that, you can pretty much tell the ghost here what to do. And it'll do this in the physical world. It'll walk to the room, it'll open the cabinet, take the grinder, put it on the table, and it'll carry out the operation, right? I don't know how well it's going to do in the physical world, but it does this quite well in a virtual world. So we sort of have extended that. I had a good game with some of the faculty, including Professor Srinath yesterday, in trying to build virtual coaches for the physical world. Especially, I wanted to get into a zone that I understand well. So I became the coach for the Purdue team. Made us go to number 11 nationally, and then I have an Olympic level player in our team, 2600. Is very very good player. So Dizzy has been working on this project for the last 3 years and pretty successful now. So now we can get a coach to come and show, and you can see the player playing. So it sort of tells you, right, only 4 basic strokes, forehand drive, backhand drive, and the 2 pushes. But a lot of table tennis is interpolation between this and learning more advanced skills, building on this area. So we have sort of been working more recently. This is a recent ICRA submission with my colleague, Yan Gu. She's a humanoid person. And I've been telling her, hey, we should do TT for 3 years. And after the first paper came out last year, said, oh, we should be doing this. So we have been working on this. Basic reward functions here are simply height of the ball over the net, target position, and reward function for moving the leg. So perhaps I would claim we may be the first or second, depending on how you look at it. UC Berkeley did something recently, and they put it out in the public. But yeah, we are going to talk about this more. But basically, the idea is, can the leg motion emerge from reward functions of hitting the ball across, and how well can we do this? So we have been, it's called reinforcement learning, but we are working on some variants of it in terms of good physics prediction of the ball, where it'll go. Can we do it with high performance vision? But more importantly, can we take that out and do it more like how humans can do, and on the head, right? So we're working on these kinds of ideas. And once the predicted ball location is known, can the motion of the humanoid, leg motion, emerge from these reward functions, right? If it can emerge from the reward functions, I can make our humanoid do better than many others to reach athletic performance, right? Not by just putting high performance compute, but being parsimonious on computing, right? After all, as humans, we don't expend much energy, and we are extremely intuitive. So sorry, I'm going to have to switch here. We'll see if my other machine is going to behave to get the more exciting part of the humanoid actually playing TT and developing this. Okay, we'll see how this goes here. Nope. It's coming. Okay. Okay, got it. Let's see if I am able to play this. And if it cooperates with me, at least you would have seen. Okay, so this is our very early test. In fact, just completed 4 weeks ago or 5 weeks ago, and you can see that it's moving its legs. It's developed both sideways motion and forward motion, and these are the kinds of things that we wanted to see. Doesn't quite do it like humans. So the question is, how much do we need to guide it as much as a coach does it with all of us, right? So we're kind of working on that space. I'm going to move past this. We'll see how. Okay, I'm kind of going to switch to design. I don't know. Can I go for 5 more minutes? Okay, yeah. So sorry about the time lap between my switches, but it's some behavior here. So we are sort of PC back. Okay. So the idea is I showed you a little bit of hands-on training and so on and so forth. We also seen a lot of work in image development. The question to us was, can I start thinking about how we can connect design and production together, right? With a lot of prior work done in image search and the emergence of both computer vision, large vision models, segmentation capabilities, and so on and so forth. So this is a very clever idea. So what Ranlan did here was just take images of a bike, right? Can we, of course, if you have an image, you can segment it easily. You tell it's a bike, it's going to describe the wheel, right? So you got the text description of the wheel, the query component. Now the question is, can we turn this text back into handles to modify the image? These are fairly easy things to do, but haven't been done in a design context. So, so you do the feature analysis. Now we bring all the frameworks. Actually, my colleagues in design are really scared of this work because the entire textbook, design book that has been written pretty much teaches a lot of these aesthetic and functional values and everything. And LLMs are able to handle this amazingly well, right? They're able to do this, and perhaps it has read all their books. So if I commercialize it, I may be sued by them. But the point here is immediately all the aesthetic handles and the functional handles, and this function form structure, people spend chapters in it. I don't want to name my colleagues who wrote these books, but they have a lot of chapters which teach this, right? And oftentimes, much of this is not used in practice at all. Some of the most creative designers that I have seen around haven't read any of these books. So the point is, if you deconstruct this, right, a chair, now I have handles. Can I deconstruct it, get the descriptions? Now I can change it. I can change it in text, and the image is going to change. How controllable? Perhaps not the best, but I have infinite number of images of chairs that I can play around with. I like some features in chair A. I like some features in chair B. I like some features in a bike. So can I repurpose the wheel in the bicycle and put it on a chair? Yeah, I pretty much did this with images, right? I generated a very large design space, right? Whether it hinders creativity or doesn't is a different question. But in doing so, I got a chair with wheels, which is what I wanted, right? I combined a bike and a chair. A lot of creativity is combination of old ideas in new ways, right? And patterns are also. So the idea is like, once I created it, can I turn it into 3D? The answer is you can turn it into 3D, right? So we sort of built on this idea, and we have shown this for many things, right? Here you're sort of playing around the shelf. So we're kind of leveraging a lot of what is going in image space, put a design framework, pretty much like how design processes are taught in classes. And then we allow people to edit it and change it in fairly seamless way, put it on that top shelf and change the handle, and then voila, you got a lot of 3D designs come out of just playing around a bit, right? And then if you throw in Tim and his team and others, perhaps they'll figure out how to produce this in a more personalized manner, perhaps. So I can get my own personalized shelf tomorrow, right? It'll change the dynamics of supply and demand, especially localizing production, because you create it, you want it, it's one of a kind, perhaps it'll get made here. It's going to be very hard to ship such products from outside. But sort of moving a little bit forward, now I talked a lot about gesture, I talked about language. The question is, can I coordinate the two? For example, I'm taking the stapler, and then I'm stapling, right? You kind of see what I'm doing, and I'm talking, right? I'm talking and gesturing and performing some actions. Can I coordinate the two, these two different spaces? Because we talk about knowledge in the physical world, but how we communicate is by doing and by talking. Can we reconstruct this back in AI? And we can reconstruct back in AI. I can talk and do, and I can create designs. So one of my really dream has been for the last 15 to 20 years is to simply get rid of my whole class. So I teach a class in toy design. It's become very large, 320 people. And the first 4 to 5 weeks, they're simply learning parametric design, how to control the features, and these large companies like PTC and Autodesk. I should say that the chair position I hold was actually started by Don Feddersen, so thanks to CAD, but my dream always has been, in CAD, computer comes first, design comes last. It should be the other way around. Design should be the focus in the age of AI. The computer should not be there. It should just vanish, right? So can I create designs just by talking? Can I get rid of the first four weeks of my class just by talking and showing? And will it create robust parametric designs? It turns out the answer is yes. So, so let me quickly jump, unfortunately, back again to the laptop. Hopefully, I get a little bit better behavior here. We'll see how it goes. I think I'll stop at this video so that I can get more questions from the team. Okay, so maybe, yeah, this is probably my last video before I finish. Oh, it's there. Okay, I got it. I think we'll end at this, so that'll be a good end of me getting rid of myself with AI in the classes. So, this is sort of combining gestures together with you know, this is a traditional CAD, right? You can kind of see that pretty much a lot of the early stages go towards creating constraints, and there's some work in this area. People have started dabbling with using text to do this, but it's not controllable. And number two, text to generation, you're not really interacting with the, oh, crap, again. So let me see if we can get this. Yeah, it came up and then went back. Oh, it's losing the, okay. We're almost there. So it's sort of losing the, yeah, what I'm noticing is it's my cursor is not moving outside my screen. So it's messing up. Yeah, it's not clear. It's just not communicating with the, yeah, there you go. So yeah, you're seeing the main part. So prior to this, what he was doing was he was gesturing the base. He said, I want to base this tall. Yeah, you see a little bit of it. He's kind of talking and gesturing together in terms of what he wants as the next feature and where he wants it. And this is a spout, creating the spout. This takes a long time to get the constraints right and you know, do the right thing, right? And then now he's got all these adjustment handles. So doing something like what he's doing now, and now he's exploring the design space, right? What else can he create? All by just talking and gesturing. And a key part of this progress here was coordinating we lost it again, coordinating the language together with the gestures. So the tokens generated by language, it's a pretty tough problem to actually make happen. So coordinating the language with gestures becomes pretty hard. And we sort of extended this, you know, can you talk to a design? Can you find out like how to fix things? Can you ask it questions? You know, can we take things that we have done in CAD and in
Assemblify allows users to interact with the assembly directly.
yeah, basically, can you talk to your design, right?
Secure and level.
Can you ask it questions on how to fix the heating coil, right?
Ask vague queries like,
Can AI together with CAD, well, I should call not CAD, but AI together with the assembly sort of come out of the design and sort of start helping people in a more conversational manner, right?
Ensuring the 3D print maintains its shape and quality.
to support clear visualization, Assemblify includes both automated and manual.
Anyway, these are our current pieces of work in both design and going back to where I started my career and starting to play around and replace some of those things which take us a long time to learn and do, perhaps not needed in the same way, right? So I want to end my talk by sort of saying that 3D plus 2D plus humans have a lot of hidden dimensions and the intersection between human and AI is kind of really, really interesting. It's a changing edge, how much humans are going to do, how much AI is going to do, which contexts are humans possibly somewhat replaceable. I think there are a huge number of bottlenecks, so the intended productivity benefits of AI are not going to happen that easily in the physical world, right? Especially when it comes to engineering. So with thanks to all my students and sponsors, so that's the end of my talk. Apologize for the connector misbehavior during it, but I think we recovered pretty well. Thanks to your staff for helping, right? Thanks.
All right, thank you, Dr. Ramani. It's open for questions. I'll come by with the mic so we can capture the question. So just raise your hand and I'll be there.
Good morning. Very nice talk. I have a question about also the biomedical applications of this, because when you showed the ability to sort of extrapolate what the extremities or fingers that are hidden can do, can that be, for example, a part of an assistive technology of people who have artificial limbs and things like that?
Yeah, absolutely. Really,
Same thing
really
like with
good
repairing.
question. Yeah.
I mean, also another thing.
Absolutely. Yeah, actually, your question is a core focus of my postdoc. He's actually working on wearable technology that exists, like EMG and EIT, to sort of look at, like in TT, right? You only have 200 milliseconds to react and plan, and you're doing that on the go, right? Your decision is not coming from here. It's perhaps coming from the so-called muscle memory we don't understand and our spine and so on. You can, people in neurophysiology and others perhaps can give you a better answer. That said, right, the so-called proprioception, which is core for this, right? Proprioception is like, what my hand is doing below the table. I exactly know what my fingers are doing. My brain perhaps my brain knows what my fingers are doing exactly. So proprioception actually works 10 times faster than computer vision. There's a Nature paper on that, not so long ago, maybe 10 years ago, right? So to your point, we are working on the athletic end of AI, right? Really pushing performance, really doing this. And the belief is, like when technology comes out in race cars, it then percolates down to other things, right? In the physical world, often you need some applications which really push your performance to see what the requirements, all the ideas in IE, like human factors and everything. What I'm finding is, what we are discovering in TT, I'm not getting answers from many of my colleagues, right? And now the kinesiology guy and the guy who's doing EMG, they want to work with me because I know how to do the AI. It's just coins turned around. Previously I want to collaborate with them. Now they want to collaborate with me, right? So to your point, the other side of it is disability and so on, right? The left hand. So my colleague in Colombia, Sunil Agarwal, he's a robotics guy. So we are starting to collaborate exactly in that same question. He understands patients, has access to hospitals. He's done a lot of work with real patients, real people, real setting. I sort of always think that any research has to be also tested in the wild concurrently. Otherwise, we live in a curated lab-based conditions, and then you want to commercialize it 10 years from now. I think a better modality to do both is in parallel, right? So we are working with that, but I have no deep knowledge in that area. But I do understand sports and athletics well. Yeah, good question. Yeah, so I think the central question that we are trying to answer there is, between perception and action, what is the difference in delay between a highly skilled person and a low skilled person, right? And seeing is not looking, right? You and I can see the same things, but perceive it and act differently, right? So what do high performance people, players have? What's going on, right? Yeah.
So thank you for the talk. I thought the really interesting with the design, the gesture and vocal-oriented design kind of reminds me of Iron Man designing the suit in the first movie, right?
In fact, that was there in the video. I didn't show you that part. Thank you.
So my question is, do you feel like that limits creativity, and what is the way to overcome that?
No, in fact, this will increase creativity. So what happens is, just like writing and other things, right? In CAD, if you're so worried about how to do the function in Autodesk and Pro E, you're not thinking about the design, right? In fact, it lets a lot of people that don't know CAD to participate in it. They may be very creative. So most people, don't go into CAD. How many people use CAD in the world today? Zero, right? Certainly in MAE. But if you look at the world, Nobody's using CAD. They don't even know what it is, right? For instance, my daughter may want something really cool, right? Can she go and talk and design it? I think yes, and I see some nodding heads, but I see the future as people that are not able to participate in design processes will be able to participate, right? Certainly CAD and other kind of tools provide environment which requires a lot of training and learning, so we want to cut that into more easily being able to design what you want. So we want to maintain your design intent in the way that you'll create a robust design, but I want to do it by talking, sketching, and gesturing, which are more natural ways of thinking. So it frees up your brain into what you want to do, what you want it to behave like, what you want it to function like, rather than learning the mechanics of how to drill down to the lowest level feature and then make that feature work.
Do you think it will, I guess to narrow my question, do you think the computer will funnel designs towards something, towards a certain corner of the design space, but avoid other spaces that are more chaotic?
Yeah, that's a really good question. In fact, it was the subject of a $50 million DARPA project where I participated. We published, and still not answered that question. So we published a paper in NIPS, Neural Information Processing Systems, where we created close to 100,000 quadrotor designs. And the idea was, can you have the human and AI to navigate the AI to spaces that you want? But certainly the question of, what is creativity between human and AI remains a big question. Will it push you to spaces? It pushes you to so many things, right? So you have a big choice. Now the problem is the other way. You have too many designs to look at, right? Which ones are better than the other, right? Can a person without the AI tool do as well? Possibly, yeah. I don't have answers to a lot of those questions, but there are a lot of very simple experiments that can be done in the human creativity area that might expose some of these limitations of AI. Yeah, they're a really good question. Yeah. But also, I would suggest the meaning of creativity is being changed, maybe not to the liking of many, right, with the Gen AI and so on. Yeah.
I guess my question is, how did you enforce geometric kind of constraints or stuff like that in the designs that you had? So you're using a generative model, but...
Yeah, certainly read the paper. A really good question. We had a conversation yesterday also. So we understand feature-based design very deeply in our lab. We participated in that generation of CAD as well, right? So constraints between features, how they work. So if you look at CAD, the most common operations there are extrude and revolve, and the generalized sweep, right? So we did it for those three. So if you do that, you pretty much get the base level CAD for most things, right? And then rounding, you just point at this and say, round me this edge. That's all it took me. That's all it took me to round this edge. Just pointing there and tell me round this edge. And give me a 4 millimeter radius there. How much time will you take to learn that operation in CAD? Right? So there's a lot of prompt engineering stacks that have to work robustly, but what the AI does is it converts my more natural way of interacting, like I'm talking to you, into a set of operations for each one of those feature sets, right? So my answer to you is, you give me $1 million, I'll make that real, but I won't guarantee that it's going to become as big as CAD today, because their infrastructure is huge and humongous, and everybody is used to it. So there'll be a lot of switching costs, but it's a research project. That's what research is about.
I guess my follow-up question would be do you think that it'll be reliant on the software backend in order for you to actually generate models that can still fit within geometric constraints? So you generated that.
All those are constraints. All I have to say is, make this round, half the diameter of that. That's it, right? Or this. So if you look at CAD, what are you doing? You're repeatedly doing these operations and making the constraints such that the modifications are robust, but also it behaves like what you want. If I can talk to it, I should be able to make it do it. Yeah. So your question is a good one. I think it's all doable. We already demonstrated the foundations. Like the first 4 weeks of my class, now I can do it in 20 minutes. So let's say every week I'm giving them one assignment, they're going to take how much time of training and how much time of doing and how much time of figuring it out. I can do that in 20 minutes, 5 for each exercise, 4 weeks. Yeah. So anyway, so yeah, that in
All
short.
right,
That's the answer.
we do have a reception for the speaker in EB3 and the third floor lobby. So if you want to continue to have a conversation, he'll be around at least for 35, 40 minutes there. So you can have cookies and coffee and have a conversation. And we are token of appreciation. We have something so he can remember us. I already gave him a bunch of goodies from MAE, but this is something that.
Thank you so much. Yeah. Thank you so much. Thank you. Thank you. Thanks. Sorry about that. That thing worked first half an hour.